Hey there, how's it going today? We're looking at 2.4 on sketching graphs of functions. Don't forget that tomorrow we will have a quiz on sections 2, 1, 2, 4, so don't forget about that. But as we look at 2.4, our objectives are two things. They're going to use the key features of functions to describe both linear and nonlinear functions, and that falls into these two standards of ACE2 and FIF4, which we've been using a few times now. And so just kind of reviewing a few key features of functions, we're going to look at the x and y intercepts. Remember, that's the points where it crosses the x-axis, and the y-intercept, of course, where it crosses the y-axis. These next two are somewhat reviewed, but positive and negative. And so what positive means is that it is above the x-axis. So we're not talking about it going up. It's just that where the graph is above the x-axis, and negative is below the x-axis. And we're talking about what domain values lie above or below the x-axis. Okay? When we talk about increasing or decreasing, we're talking about now the direction in which the graph is going. Is the graph going up? Is it going down? And so as we look on a graph, as we go from left to right, as we're going across our graph, if the y values are increasing, then the graph is increasing. And same is true if the y value is decreasing, then the graph is considered to be decreasing. The last thing, we talked about this the other day, in behavior. Remember, the in behavior is where this goes as x goes to positive infinity or x goes to negative infinity. And so we're going to use this information to sketch graphs. And so we're going to look at this first example here. Given the key features of a linear graph, we're going to sketch this out. And so we're told that the y-intercept is 2. So the y-intercept is 2. It says the function is positive when x is greater than negative 1. Now remember, we could see that in interval notation. We could say it's positive from negative 1 to infinity. In this case, so you might see that notation. But if it's above the x-axis, so at negative 1, that means it's got to touch the x-axis. And from that point on, it is going to be above. So all of this is going to be this way. Now, we were told it's linear, right? So if I've got 2 points, I can now just go ahead, connect my dots, draw the line. We're also told that the function is increasing. So that means as I go from left to right, it's increasing. That part matches. And we're also told that as x goes to positive infinity, f of x goes to positive infinity. That's true for this piece we've drawn. But we're also told that as x goes to negative infinity, f of x goes to negative infinity. So what that tells me is that this piece continues through the x-axis now in this direction. And so we don't even just get a sketch. We actually get the actual graph of the function based on just that information. There is one line that matches this because, again, it is linear, not anything else. So let's look at a second function. This one's a little bit different in that we're restricted in our domain and range. And so we're going to start out with the same pieces. We're going to start out, we've got a y-intercept of negative 3. So we're going to take our y-intercept of negative 3. We're told it's linear. The function is positive for when x is greater than 1.5. So at 1.5, I'm going to be crossing the x-axis. And I know from this point on, it's this way. Again, we're linear, so I know I can connect these 2 points and start to make a line. It's increasing for all values of x. And so, again, as I go from left to right, that's true there as well. But here's where the change comes in, and this might trip some of you up. We're told that the domain is from negative 2 to positive 3. And again, we might see that domain given in interval notation like this. And so what that does is it restricts what x values this graph can have. And so I'm going to put in some dashed lines here where this graph is going to start and where it's going to end. Anything to the left or right of these red lines is not in my function because it's not a part of my domain. We're also told that the range is from negative 7 to 3. And so as we look at that, again, we could see it in interval notation with brackets here, negative 7 to positive 3. And so I'm going to do the same thing. I'm going to have a line there, and a line there. And so what that means is my blue line is going to be increasing up to here. And it'll actually hit this corner. As I'm coming down, it's going to hit this corner here as well. And so when we look at the slope, again, my line's not perfect, but had I drawn it perfect, because this is up 3 and right 1.5, so again, up 3, right 1.5 does hit that corner. Down 3, right 1.5. I end up close to that point. We should hit that point exactly in the end. So if we're given a domain and range, we have to restrict our graph to fit within a certain box. And our box that we're fitting in this case is this box right here, because we've got to be inside that box based on this domain and range. If we're told that like x is greater than a certain value or y is less than a certain value, then we won't be inside a box necessarily, but we will be restricted to not the entire graph, but the portion of the graph that meets that domain and range. So let's talk about nonlinear functions. A couple things coming out here. We got continuity, and remember we talked about discrete and continuous functions the other day. And so a function is continuous if it's graphed with connected lines or connected smooth curves. So our linear functions that we had in the first two examples, those are continuous. They have continuity. Again, a discrete function would be either broken up into pieces or would be individual points along the graph. The second definition we're coming back to again is extrema. Remember we talked about this one as well. These are the maximum and minimum values of the function. They could be relative max and mins, or they could be global max and mins of the entire function. And the third thing that we're talking about here is symmetry. Remember, symmetry is if I'm able to draw that vertical line that divides the graph into two halves that are mirror images of each other. Again, we talked about point symmetry as well. But for most of these graphs that we're doing, we're going to be more focused on line symmetry and not point symmetry. We've got a couple of examples here of nonlinear sketches. And so the idea is still the same. The idea is that we're going to graph this up based on the information that we know. So we're told the function is continuous, which means it's one smooth line or curve. We're told that the y-intercept is 1, so my y-intercept is here. The function is positive from -1 to 3. And again, we might see that in interval notation, -1 to 3. And so that means I have an x-intercept at -1 and an x-intercept at 3. And so we start to get an idea of a picture that might be happening here. Now, I'm not going to make a straight triangle, but we might get some type of graph that goes like this. Again, we don't know that for sure yet until we read the rest of the information. The next piece says that the function has a maximum at 1, 2. So 1, 2, I'm here. And so now I've got another piece of information. Now, it looks like these 3 points make a line. And let's see what else we're told. It says the function is decreasing when x is less than 1. So, increasing when for x less than 1. So anything up until I hit here, it is increasing. And so if I'm following these points, it looks like it's going to go like this. And then we're told as x goes to infinity, y is going to negative infinity. Well, that makes sense to go from this point to this point and then be able to continue through this way. And as x goes to negative infinity, that's going to the left, y goes to negative infinity as well. And so we get this function, this absolute value function. Now, we weren't told that it wasn't an absolute value function, but 3 distinct points all making a nice line lead me to believe that this is a absolute value function. So we now go to example B, and the function is continuous and symmetric about the line x equals 1. So I've got a line of symmetry at x equals 1 coming through like so. So whatever happens on the left is going to happen on the right. And so when we start graphing these points up, we're told it has a minimum of 1, 0. So 1, 0 is here. And we're told that as x goes to infinity, y goes to infinity. So somehow it's going up this direction. And as x goes to negative infinity, y goes to negative infinity. So somehow it's getting up this direction. And so we're not told what we have to graph here. All we're told is that the function's continuous and symmetric, and then the end behaviors. So I could have some type of graph that looks like so. Now, again, it's got to be symmetric, so I've got to mirror this out this way as well. And so I could have any kind of graph that I want in here. Again, it could just be a nice little v, it could be a parabola, or it could be some other powered function that we have in the end. But the key is that the end behaviors must match. As x went to positive infinity, the y had to go to positive infinity. And as the x went to negative infinity, y is going to positive infinity. All right, so let's look at our last example here, a nice real-world sketch. And so we're given a lot of information here. And again, the key is to decipher it all and build your graph. And so when we look at this example, we're told that given the key features, sketch a graph. Billy goes for a bike ride on a path near his house. We're first told that the y-intercept is 0, so I've got some type of coordinate plane, and we need to decide what our x and y's are. Now, if we're riding our bike, or riding a bike, we'd have distance, rate, and time, right? Because that's be the three things that we could use. Well, we're told the y-intercept starts at 0 miles per hour, and then we're told that Billy starts at 0 miles per hour, and so our two axes, our x-axis is going to be time, and our y-axis is going to be speed, because again, we're starting out on this bike ride. And so we started at 0, 0. Now you see I haven't labeled out any time hacks yet or any speeds because we haven't gotten through the rest of the problem. But as we build this out, we're going to see his maximum speed is 20 miles an hour. So I'm going to go 5, 10, 15, 20. And our speed's in miles per hour. And as we start looking at the time that is taking this, we've got 2 minutes here, 2 minutes here. But those are actually the same 2 minutes as we read through this problem. We're at the 10-minute mark, another minute, so that's 11. And then he stays there for 5 minutes, so now we're up to 16, now we get to 17. And so it looks like we need to go out to 20 in time, so 5, 10, 15, 20. These are in minutes. And so as we build out these pieces, function's nonlinear. Now that doesn't mean individual pieces of it couldn't be linear segments, but the entire graph is not one nice line. And so his maximum speed is 20 miles an hour, which he reaches after 2 minutes. So 1, 2, 3, 4. So at 2 minutes, he reaches 20 miles per hour. And we're told that his speed increases steadily, which means if it's steadily, it's a line for that piece. We're then told at the 10-minute mark, he decreases his speed. So we're going to assume here, because we have no other information to prove otherwise, that his speed did not change until the 10-minute mark. So at the 10-minute mark, he goes straight out because the speed didn't change. Now, that doesn't mean he's not moving because he's going at 20 miles an hour, so he's going somewhere on this bike path. Now, after the 10-minute mark, he decreases his speed for 1 minute and then stays at 10 miles an hour. So from minute 10 to minute 11, so it's 11, 12, 13, and 14, at minute 11, he's down to 10 miles an hour for 5 minutes. So now he's here for 5 minutes. So 5 minutes from 11 would take us to 16. And so that's going to keep us steady there. And then after this time, he decreases speed for 1 minute until he reaches a stop. So at minute 17, he has finished his bike path and he has stopped. And so this is the picture that we would get from this function. That's it for 2.4 on sketching graphs of functions. The word of the day is pep rally because tomorrow is a pep rally for y'all. And so again, the word of the day is pep rally. Hope y'all are excited for tomorrow and all those that are participating in it. Don't forget, if we have enough students here, we will have a quiz tomorrow. If not, that quiz will get pushed to Monday. Y'all have a great one. Stay safe with these storms coming through today. Bye.